In this video, we're going to talk about prime factorizations, and I'll do a few for you so you get a feel for what it's like to break a number down using a factor tree. Just as we found all the factor pairs in factorizations. Okay, and I made a video on this, and I showed you how to create factor pairs of a number. We're going to kind of do the same thing, except we're only going to keep prime numbers. So, just as we found the factor pairs in factorizations, we'll find all the prime numbers that multiply to give a specific number. That result, the result is a product of prime numbers called prime factorization. That means that when you get done, you will only have prime numbers that multiply together to give you that number you started with. Only prime numbers. Only numbers whose factors are 1 in itself. So, this important concept culminates with the fundamental theorem of arithmetic that says each and every natural number has a unique prime factorization, meaning that 60 has a prime factorization that no other number has, ever, anywhere. Okay, so now, first of all, let's go ahead and kind of list out some of the numbers that are prime, because we want to have a good idea of what we're looking at. So, as we list them out, 1 is not prime, 2 is. In fact, it is the only even prime number. 3 is prime, 4 is divisible by 2, 5 is prime, 6 is divisible by 2 and 3, 7 is prime, 8 is divisible by 2, 9 is divisible by 3, 10 is divisible by 2 and 5, 11 is the next one, then 13, then 17, then 19, then 23. Okay, that's going to get us a pretty far look as to what numbers. Primarily, right now, we're just going to concern ourselves here with the bottom 5-ish. We might get into 13, but just kind of ease into it. So let's go ahead and start with these. We'll do a couple examples here. I'm going to keep my prime numbers up here handy so I know what I'm doing. And now, at this time, if you don't know what an exponent is, I really would like you to go back and review what it means to be an exponent. So let me write that word down here so you can search it. Exponent. Because we're going to use exponents to show repeatabilities in multiplication. And I'll explain it as I go. However, you might want to find a video or just an explanation of what exactly an exponent does. All right, starting with the number 60 here. I'm going to start just like I did in factorizations. I'm simply just going to start off as a factor pair. So just a tree with 2 branches. And I'm going to come up with 2 numbers that multiply to 60. Well, since 60 ends in a 0, I know that 10 is one of those factors and 6 is the other. Neither of those, however, are prime numbers, so I'm going to break them up even further. 6 is 2 times 3. Each of those is in our list of primes. 10 can be written as 2 times 5. Each of those is written into our primes. If it makes you feel better, stick the multiplication symbols in between each. And now, we count the number of multipliers that we have. And so I have 2 2's. I have 1 3. Right here, and then I have 1 5 right here. And so the prime factorization of 60 is 2 squared, or 2 times 2, times 3 times 5. No other number will have this factorization. Let's do another one. 28. Now, one way that makes it a little easier to do these, perhaps, is when you notice it's an even number, rather than trying to break it down into 2 big numbers, start right out with a nice prime. So 28 can be broken down into 2 times something, which is 14. 14 can be broken down into 2 times 7. And so now that only primes exist, I have a 2, and I can bring this down. So I have 2 times 7. I have 2 squared times 7. And that is the prime factorization for 28. So let's use that technique on 168. I have the number 2. And so 2 times what? Okay, well 16. 2 times 8 is 16, so since it's 160, it's really got to be 2 times 80. So if you divide this out, you're going to get 84. And then I'm going to break down 84. I'm going to break it down into 2 times 42. And then I'm going to break down 42. I'm going to break that down into 2 times 21. Then I'll break down 21. I'm going to break that down into 3 times 7. And now 3 and 7 are both prime, and all the 2's are prime. And so as I bring them down, 2 times 2 times 2 times. And you notice how they just kind of fall down. Okay, well now just simply count the number of multiplications. 2 times 2 times 2 is 2 cubed times 3 times 7. That is the prime factorization for 168. You notice they're close. Some of them are close, but they're not exact, and that's what that fundamental theorem of arithmetic says. All of these numbers will have different prime factorizations.